So we are about to enter the world of Laplace transforms, and we're going to see that sometimes we can take a differential equation and we can apply a Laplace transform, and that will allow us to solve the differential equation a little bit easier than what we would be able to do with other techniques. So let's talk about the definition of Laplace. Definition 7.7.1, the Laplace transform, we're going to let f be a function defined for t is greater than or equal to 0, and we're going to have to integrate here. So the Laplace transform, and they're using that curly L of f to signify you've taken the Laplace, and it's really just an integral. We're integrating from 0 to infinity of the function f of t times e to the negative st dt. So this is the definition for a Laplace transform of f, provided that this integral converges. So we're going to see a lot of those things from Calc 2 pop up in this section. So just some definitions and some terminology and some notation here. Anytime you see that curly f, that means you want to take the Laplace of what follows. The capital F of S tells you you have a Laplace transform for f of t. So the same thing here, if we're using g of t as our function and we apply the Laplace transform, that capital G of S says we have the Laplace transform of g of t, and then we could do it with y of t as well. That capital Y of S means you have the Laplace transform for y of t. So let's look at a few examples. So we want to evaluate the Laplace of 1. So under this definition, we want to integrate from 0 to infinity of e to the negative st times the function, which in this case is 1, dt. So this is going to require us to apply the limit as b goes to infinity, and we're going to replace that upper bound of infinity with b. So when we integrate this guy, remember t is the variable we're integrating with respect to, so we're treating that negative s as a constant. So thinking about a u substitution here, if u is negative st, then du would be negative sdt. We are missing the negative s. We can compensate with a negative 1 over s out here. So now when we integrate, integrating e to the u becomes e to the u, and then we need to evaluate from 0 to b. So then we have negative 1 over s, limit as b goes to infinity, using that fundamental theorem of calculus. Remember, this guy's going in for t. This is e to the negative sb minus e to the 0. So I'm going to rewrite this. Just rewriting that e to the negative sb as 1 over e to the sb, and then e to the 0 is equal to 1. So now we want to apply that limit there. We've applied the fundamental theorem of calculus in the step before. Now we want to apply that limit. And we want to know what's happening as b goes to infinity. Well, as b goes to infinity, that term in the denominator is getting larger and larger and larger. So that guy's heading to 0. And that 1 here is still heading to 1. So we have negative 1 over s. 0 minus 1 is a negative 1. So this guy is heading to 1 over s. So then we say that the Laplace transform of 1 is equal to 1 over s. Now, usually we want to talk about where that integral would converge. For what values of s will this force convergence? Well, if we think about this here, and it may be easier to think about these possibly in this step, I would say. So if that s, that exponent on that e, if this were to be, how do I want to explain that? If that s is going to be positive, thinking about this step here, then as b gets bigger and bigger and bigger, so remember it's heading to infinity, and it will always head to infinity because of that definition of what a Laplace transform is. So as that b is getting bigger and bigger and bigger, if that term is in the denominator, then that's going to force this term in the denominator to get larger and larger as well, which in turn would take this and force it to go somewhere. And in this case, that somewhere is going to be going to 0. So as long as s is positive, then that's going to force this to go to 0, which is going to force this entire integral to converge. So I do want you to notice that this guy is going to diverge if s is less than 0. Okay, so think about it here. If s happened to be a negative number, and we could plug in any negative number like a -2. If s were a -2, then we would end up, and b is going to be positive, then the exponent would be negative. So this guy would actually be in the numerator. And if that's in the numerator, as b's get bigger, as b is getting bigger and bigger, then that's going to diverge because that guy is going to head off to infinity. So we want to force convergence here, and we want to think about what would s have to be to force this integral to converge. So we're always thinking about that in the back of our minds. So in this case, s would have to be greater than 0 to force that convergence. Let's look at another one. Let's look at this guy. We want to find the Laplace of t. So applying that definition, we're integrating from 0 to infinity of e to the negative st times t dt. So if we want to integrate this, we're going to have to do this guy by parts. So thinking about our u and dv here, we could let u be t. So dv would be the leftovers, e to the negative st dt. So our u, if we take the derivative of t, we're going to get 1 dt. If we integrate v, we're going to have to think about that u substitution again. We need a negative s here, and we would compensate with a -1 over s. We're thinking about the integration. So that's going to give us a -1 over s e to the negative st. So by parts, when we integrate, we're going to get uv minus the integral of v du So I'm going to clean this up just a little bit, and then we'll evaluate from 0 to infinity. If I pull that -1 over s out, we get that. U substitution again. Our u is negative st. du would be negative s dt. Compensate with a -1 over s out here. So we're going to have -1 over st e to the negative st minus 1 over s squared e to the negative st, and we want to evaluate from 0 to infinity. So I'm going to rewrite this in terms of that limit notation. So we could think about it this way. I could have used the limit notation up here also in the beginning and done the rewrite. But I wanted to do the by parts first in the integration. So now if we do that fundamental theorem of calculus, remember these are going in for t. So we have negative 1 over s times b e to the negative sb minus 1 over s squared e to the negative sb. Subtract. And then if we plug 0 in to that first one, we're going to get 0. Remember, it's going in for that t. Minus 1 over s squared e to the 0. So I'm going to do a rewrite here. So we have negative 1 over negative 1b over s e to the sb minus 1 over s squared e to the negative sb. Now minus negative there turns that into a positive 1 over s squared, and e to the 0 is 1. So if we apply that limit, we would take the limit of each piece separately. This is 1 over s squared e to the positive sb. There's a typo there. Let me correct that. Plus the limit as b goes to infinity of 1 over s squared. Alright, so let's do the last two pieces first. This guy's easy. There's no b in here. We're treating this as a constant. That's just 1 over s squared. This guy's easy because as b gets bigger and bigger, that denominator is getting bigger and bigger, so that guy is heading to 0. This guy is going to require L'Hopital's. So we're bringing back a lot of good memories from Calc 2. So L'Hopital says if you want to find that limit, you can take the derivative of the top and the bottom separately. Because the top's going to infinity and the bottom's going to infinity, this guy is in the indeterminate form infinity over infinity. So if we were to take the derivative of the bottom, remember we're doing it with respect to b. So this is going to be s e to the sb times the derivative of that exponent, which is an s, which turns that into an s squared. And then that limit will end up in turn going to 0 because that denominator is getting larger and larger and larger as b gets bigger and bigger. So this guy is heading to 1 over s squared. So then we would say the Laplace of t is equal to 1 over s squared. And let's talk about what forced that convergence. So if we go back, we really could think about it in terms of this step, or we could think about it in terms of this step. A lot of times it's easier to think about it in terms of those positive exponents, which that term's in the denominator. So for this to converge, this guy wasn't a problem at all. It's really talking about these pieces here, those exponential pieces. As long as that s ends up being a positive number, then it's going to converge. So x has to be greater than 0 here. If s were a negative number, so let's say again it was like a negative 3. So let's write out what that scenario would look like. We would have negative b over se to the negative 3b. And we're asking what if s was equal to negative 3. What would that convergence look like? minus 1 over, if s is a negative 3, I'm just going to replace all of them with a negative 3. Check out what would happen here. We're taking that limit as b goes to infinity. So, and we're asking, what does s have to be so that we can force the convergence of this integral? So we said s has to be positive, but now we're asking, well, what would happen if s were negative? And we're just randomly picking a number, like a negative 3 there. Check out what would happen. If that s was a negative number, like a negative 3, then this guy, because it's negative exponent in the denominator, that guy really belongs to the numerator. So as b gets bigger and bigger, this guy's going to head to, in this case it would head to negative infinity because the negative there, but it's still not heading to a number, it's diverging. This guy would end up diverging as well because this really belongs in the numerator. We could rewrite that as e to the 3b. So then as b is getting bigger and bigger, that guy's heading to positive infinity. This guy would still converge, but if the sum of the, or the difference of the first two terms doesn't converge, then that whole thing is not converging, is diverging. So we always want to think in the background, what does s have to be? Where does it have to go to force convergence? Because we're all about forcing that convergence here. Let's do another one. Let's look at example 3. So we have 2 of these we want to find. Let's look at that first one. A is asking us to find the Laplace of e to the negative 3t. So if we use our definition and we're going from 0 to infinity, of e to the negative st, e to the negative 3t dt. So when we multiply and that we have the same base, we add the exponents together. And since those both have a t in common, I'm going to factor that t out. So we have negative s minus 3 there, t dt. So thinking back to Calc 2, we're going to take the limit as b goes to infinity. We're integrating from 0 to b, e to the negative s minus 3 t dt. So remember your u substitutions. We would need a 1 over negative s minus 3 here. And we can compensate with a 1 over negative s minus 3 outside. So then when we integrate, we would get 1 over negative s minus 3 times the limit as b goes to infinity of e to the u and then we're going to evaluate from 0 to b. So I'm going to rewrite this. We could factor a negative out of the denominator and then move that negative to the top. So we could rewrite that first term that way. I'm going to do the same kind of thing over here. If we were to factor that negative out, it would look like this. And then we could rewrite this way. And keep in mind we're going from 0 to b. So now let's plug those limits in and use that fundamental theorem of calculus. When we substitute that in, we have 1 over e to the s plus 3 times b. I have a typo there. That should be a t. Minus 1 over e to the 0. Remember, e to the 0 is 1. So we have negative 1 over s plus 3. And let's apply that limit. So if b is getting bigger and bigger and bigger, so b is heading to infinity. There's some typos here. Let me correct those. Remember, b is heading to infinity here. Okay, so we're taking the limit as b goes to infinity. All I've done from this step is move this term to the denominator because I had a negative exponent. So it became this. b is still heading to infinity. If we use that fundamental theorem of calculus, then we would have this guy. So then as b gets bigger and bigger, that first term is getting smaller and smaller and smaller. So that guy's heading to 0. Just because that denominator is growing without bound. This guy is really 1 over e to the 0, so that's 1 over 1, which is 1. And as b gets bigger and bigger, it's still heading to 1. So this guy's heading to 1 over s plus 3. So let's think about that convergence. What would s have to be to force convergence here? Well, we want, and I'm going to go back to this step here. I think it's the easiest way to see it. We want that to be a positive number. So s plus 3 has to be bigger than 0, which means s has to be greater than negative 3. So as long as that s is greater than negative 3, then it's going to force this definition to converge, which means our Laplace transform for e to the negative 3t would be equal to 1 over s plus 3. So let's do another one. Let's look at part B. And I'm going to go back a page so I have more room to write. B is asking us to find the Laplace transform of e to the 5t. By definition, we're integrating from 0 to infinity of e to the negative st times our function. In this case, it's e to the 5t. So we can combine these using exponent rules. When we multiply and we have the same base, we're going to add the exponents together. So that's negative s plus 5 times t dt. So I'm not going to use that limit definition on this. I'm just going to do this shortcut way, but I think you'll understand why I'm doing that. So let's think about our u substitution here. So if u is negative s plus 5t, du would be negative s plus 5. So we need the du here, and we can compensate with a 1 over negative s plus 5 out here. So then when we integrate, that negative 1 over negative s plus 5 is out here. When we integrate e to the u, we get e to the u. And we're evaluating from 0 to infinity. So I'm going to rewrite some of this. That negative, if I factor a negative out of the bottom, I would have a negative times s minus 5. I'm going to factor a negative out here also in that exponent. And then I'm going to move that negative to the top just to clean it up a little bit. And then I am going to rewrite that exponential as 1 over e to the s minus 5t. And we want to go from 0 to infinity. So I'm not using that limit process here. I am using the limit process, but I'm not writing it out. So let's think about what happens as this guy gets bigger and bigger. Oops. So we have e to the s minus 5. If we were to plug infinity in here, notice that that exponent's getting bigger and bigger and bigger. If we were to plug 0 in here, we would have e to the 0. So this guy, that denominator is getting bigger and bigger because that exponent's getting bigger and bigger, but that whole fraction is shrinking. So that whole fraction is heading to 0. This guy is just heading to 1. So we can get that same idea of what's happening without writing out all that limit stuff. If you do want to write the limit stuff out, feel free to. I am good either way, however you want to do it. So what I really want to see is, do you know how to do this and where is this going? So simplifying, we get 1 over s minus 5. So we would say that the Laplace transform of e to the 5t is equal to 1 over s minus 5. Now let's talk about where that works. And that's really going to take us back to, we could see it here thinking about that exponent. I think it's easier probably to see it here. We want this guy to be positive, because if that s minus 5 is positive, then this term stays in the denominator. So if s minus 5 has to be greater than 0, then s has to be greater than 5. And that would force convergence for this guy.